and became very important for this eclipse that occurred the next year, 1986. There was an eclipse which caught my attention when I was probably about 13 years old in this classic publication by Giméus and collaborators, their canon of solar eclipses, where this eclipse in 1986, which is an annular total eclipse, was listed as a 0-second duration eclipse. At maximum, it was annular, became total for 0 seconds, and then became annular again. And this is because the moon's shadow, the apex of it, just barely, or maybe didn't, touch the surface of the Earth. It was just that perfect confluence where the angular diameter of the sun and the moon were exactly the same size. Other computations, and Fred has looked at this independently, and we've talked about it over the years, have shown that this eclipse that occurred in the middle of nowhere off Iceland had a maximum predicted duration of just about 0 seconds. If you want to split hairs, minus 0.2, so maybe it really wasn't total. It was only a few 100-meter wide shadow, so it became important to predict these accurately. That's at sea level, but if you can manage to get up into the apex of the moon's shadow, which brings you, in this particular case, 80 miles closer to the moon, the shadow gets a little bit wider, but you're closer to the moon, so the moon's angular diameter grows and gives you a little bit more closer towards totality. So we tried to do this using some of these new enabling technologies that have been put in place over the next 20 years. We had the computational power to predict when and where. We had aircraft available that we could use. Could we do it? It was a very difficult sort of a thing to implement. The uncertainties, the predictions, the methodology was known, but the actual measurements of the moon's limb have not yet really been codified in a way that were available very well. Alan Fiala providing this from the Naval Observatory, saying this was a new program. He didn't know the exact scale. Before we were talking about the scale of the solar system, the exact scale for calibrating this wasn't that well known. The models for atmospheric refraction, they're models, and it changes depending upon what the atmosphere is actually doing. And GPS satellites didn't exist. Aircraft didn't fly by GPS back then. So we took a chance, we did it, and we saw this spectacular event that to this day, I don't know whether to call it a total eclipse, an annular eclipse, a hybrid eclipse, or give it a name. But we saw a ring of chromosphere punctuated by beads, and the time scale from here to here was about 8 or 9 seconds, going from what you might call second contact to third contact, a truly, truly amazing event. And the observation of this was only brought about by the emergence of these new technologies coming together. But this was the mid-1980s, and portability continued, capability continued, and I personally got involved in a number of aspects of using these new capabilities to make them more available to other people. First, there was a migration into the graphical user environments that were becoming available with, for example, the Macintosh and other computers that were starting at those times, making a more user-friendly interface for these sort of things. There was also a real desire on my part to automate taking pictures of eclipses. I hated going to eclipses and being a slave to operating cameras. So the early prototypes were based on earlier generation computers. This was 6502 processor, which was a little bit lower down on the Moore's law curve, but was used by me originally to prototype a system for automated eclipse photography that I used for the 1991 eclipse in Mexico. And that was relatively easily ported then as an underpinning to other developments. In parallel with that, really portable computers came out, the first laptops in the early 1990s. That made putting these eclipse prediction systems, calculation systems, out of these big mainframes and onto laptops, and you could take them, and in this case, combining two key elements, wanting to watch eclipses from the air to get above nasty weather and get to places when you couldn't see it from the ground because of logistics, with being able to recompute things in situ, actually in response to wind and so forth, and get accurate eclipse predictions and fly through it. So this first E-flight software was used in 1992 for a flight with a DC-10 at 41,000 feet, and was able to prolong totality from about 4.5 minutes to 6.25 minutes. And this is the same software that had been updated over the years that Space had used for the eclipse flight they had recently done from here in India. So at about the same epoch, again, this was all sort of parallel work, was porting, moving this centerline eclipse computation software, hybriding it with the hardware control into a system that ran on laptop computers that could interface with just about any camera, and was first tested for my own use here in India, the eclipse in 1995, and it worked extremely well, because for that very short 52 seconds I was able to watch the eclipse and not have to worry about taking pictures of it, just processing them after the fact. This particular system that I talked about at the last solar eclipse conference, I think, is now somewhat obviated. Xavier has now a much more, I won't say robust, but more modern version running on Macintosh computers. Sort of predicated on this, but he's taken it a step further, integrating it with map visualization and other tools. And talk to Xavier if you want to see the most recent version of this sort of control software. But the reason for doing this was for taking multiple exposures in an optimized way for then linearly combining or non-linearly combining these things for high dynamic range imaging that could be done using computational tools that didn't exist before. The eclipse flight software was enhanced for use, in particular, knowing that there was a big eclipse coming up in 2001 that there was a possibility of using a Concorde for, and it had not originally been thought that we could actually outfly the moon's shadow in commercial aircraft, but clearly we could with the Concorde when it was flying. So a century made a big difference from 1903 to where we were at the turn of the 21st century, contemplating supersonic flight for anybody to use. There was one in 73 for scientists. And in roughly the same size observing platform, moving these big 135-foot telescopes into little distributed instruments that in some sense could do as well or better for high resolution and other imaging studies. So from this point, I actually just want to talk about the implementation of using some of these technologies for eclipses that I have seen and done. And as I say, the first we planned was a supersonic flight with the Concorde. There was a maximum duration of about 5 minutes of this eclipse, but the geometry was such, it almost repeated the 1973 Saros predecessor a bit further south, and we would have been able to chase it for over an hour. If you look at this graph, this is the velocity of the moon's shadow as a function of time. The dotted line here is the cruise speed of the Concorde, and you can see that the Concorde actually can outfly the moon's shadow. You have to slow it down. This would have given us the capability for an hour totality, and actually to adjust the speed of the aircraft and sort of hang the diamond ring in the sky for about 4 minutes and sit there and watch it. We were planning on doing this supersonic eclipse flight. We had an agreement with Air France. We got permission from the governor of Ascension Island to launch the flight from there. And then unfortunately, as many may remember, there was the accident outside of Paris in 2000 that grounded the fleet, and everybody on board had perished in that. And that was the end of that. Something that we had wanted to do, but obviously we're not able to proceed with. So the plan then instead was to do this from the ground, and we picked an observing site in Zambia in Africa off the Zambezi River. A change of idea of what we wanted to do for imaging then. It was very close, only 130 kilometers by road, but the roads were not always so cooperative. Modern technology doesn't help when you have to get there on pontoon bridges, and eventually we got there. Roads were a little bit better than in Delhi, but I was surprised by the traffic here, I have to admit. No traffic there, but hard to get to. And we got to our base camp along the Zambezi River, upriver to the eclipse site, some of the locals upriver that were keeping an eye on us as we were keeping an eye on them. And then deploying some of this consumer and home brewed and put together in small laboratory or garage type equipment with a number of imaging goals that have continued to be pushed, eclipse after eclipse, making things better. We heard this theme before, high dynamic range imaging, coronal polarimetry, and actually just taking pretty pictures. So 3 cameras used, all controlled by one central computer, all available to be done now, all hands off, automatic tracking. And the results of that eclipse with some of the locals watching what was going on. The second contact diamond ring, exactly as predicted, as today we just expect. We expect to be in the right place, we expect to be in the right time. Contrast is a little hard on the screen. I have some pictures up on a poster you can see later. It's, the lights make it a little bit difficult to see. The transition, contact 2 transition sequence taken from this imaging camera, executing this exposure ramp. It's nothing more than bracketing, but being done on a log normal sort of exposure ramp, which is optimal, what you want to use for combining images to bring out the structure over large dynamic range. And in this case, this was with some spatial filtering to look at the inner and mid-corona. Same sort of thing on a wide field camera to get to the outer coronal regions. That was only sort of for the inner 1 degree or so field of view. And what used to be done with radial gradient filters, laboriously made in laboratories and applied into camera focal planes, was now all done digitally by combining these, again, using this processor technology that had become available. I think this was pre-Photoshop. There's different algorithms that were used, but basically the same sort of image combination techniques that were used. Particular interest of mine is looking not only at the structure of the corona, but to understand the physics of what's going on. There's another aspect of this is you can do polarimetric imaging of the corona. You can measure the electromagnetic field of the sun by taking polarized images of the sun, just taking a Polaroid filter, rotating it 60 degrees between images, which gives you a particular view of the solar magnetic field. From that, you can compute what are called the two linear polarization states, which kind of gives you a picture of what the magnetic field is doing in the two orthogonal directions. You can put that together with some computation. It gives you a measure of the polarization and the direction of the magnetic field, and those two together actually gives you a total intensity image, which is like an image of the eclipse, but also measures how much of the flux, how much of the energy of the light is polarized in that region. And that actually gives you a map of the electromagnetic field strength and the direction. And this is actually a student experiment that can be done very easily by taking a camera and a Polaroid and just rotating it. And we've got software that this can be done. And this is extremely useful to trying to understand the physics of the corona. So polarimetry is a particular interest of mine. And if people want to talk about that, I'm happy to talk to them about that. Following that, the 2002 eclipse was almost really a purely aesthetic one from my perspective. I met Joe Calley, who's in the audience, and will be talking to us about the next eclipse in Australia. That path was across southern Africa, across the ocean, and ended at sunset in Australia. And there was an opportunity here to see a total solar eclipse very, very close or at sunset at the end of the path. And the desire here was to see low-altitude shadow phenomena. What does the umbra really look like in the sky when it's viewed from a very low angle? Daniel Fisher will tell us more about some of his recent experiences with that. The probability of clear skies here was actually very, very good. This is the problem with observing from a low-altitude eclipse, is you're looking through a lot of air mass, and you normally would have a lot of cloud. But here in this particular part of Australia near Cameron's Corner, at the time it had been bone dry. It hadn't rained for 2 years. It's a desert-like environment. It's very dusty, but cloud was unlikely, although we did have some that we had to deal with. So it was about a 3,500 kilometer trip over 4 days there and back to the eclipse site, with a reliance on these technologies that we almost took for granted by this point. The Iridium satellite constellation had been deployed, so in the middle of nowhere where there's no cell phones, we had satellite coverage to call back and get information as we needed making the trip. The GPS satellite constellation had been deployed, and so again, when you're in the middle of nowhere and you're looking for centerline and you pull out topographic maps that have nothing on it to cite, it's really nice to get yourself accurate to 10 meters or so just by pulling out your GPS, or I suppose today you could do it with any sort of handheld GPS device. And the visual and infrared imaging satellites able to give us a look from above on the cloud situation. And so these are the sort of integrated technologies that are made eclipse chasing much more tenable, and of course use of aircraft. Here we were not using aircraft to chase an eclipse, but having them on standby nearby just in case the weather was bad, which it wasn't. It cleared out as expected, and we had beautiful clear skies. A bunch of people, some in the audience here, putting together these technologies, the cameras, the automated cameras. Some new digital cameras were coming online, controlled by a single computer, could run these things much like they were in the African eclipse. You know, are we a cult? Are we a culture? I don't know how many people you see doing these sorts of things, putting weird equipment together in the middle of the desert in Australia, getting ready for the eclipse. The local folks, the Ogilvies, it was their facility, their ranch they let us set up on, and it was quite an amazing thing to have everybody join us then. So that eclipse was imaged by these cameras. This is the transition into totality. The shrinking of the solar crescent 1 second apart, and the visualization starting of the inner solar corona. And this gold coloration was actually due to the dust in the atmosphere. Lots of dust. We expected that. It was actually very pretty, giving rise to this golden corona at second contact. And of course, this was a very short eclipse. It was about 26 seconds. But it was a marvelous view down at the horizon. Bengt Alfredson, who's here, took this photograph, which shows the umbra and the perspective of looking down the umbral cone when you're very near the end of the throat of it at sunset. So this is the umbra framing the sun, chromospheric light, light from the chromosphere on the horizon, and this is outside of the umbra, which we're enveloped in here at this point. As third contact approached, it was a very narrow eclipse path, so we had quite a bit of chromosphere, almost 180 degrees. And you can see the transition back in the near 26 seconds after totality with the diamond ring against this sort of golden corona. Pictures of third contact, but what was most remarkable with this eclipse was actually seeing the moon shadow. These are photographs taken by Joe Calley, who's here at the conference, and you'll hear from him as well. Remarkable series of photographs, in my opinion. You can see the total eclipse here in this all-sky camera. This is looking at the whole sky up above you. You can see the umbral shadow, and behind us, outside of the umbral shadow, and it transitioned up because we were at the end of the shadow and the moon shadow was going back into space, and here's the transition, watching the shadow over us, leaving, not to come back to the Earth for another 354 days. A truly remarkable thing to actually see, the lunar shadow like this. We had a really very, very pretty sunset, just a pretty thing to watch from the Australian desert. And then 354 days later, we had another challenge. This was an eclipse that was really in the middle of nowhere. It was in Australia, and we heard about how at the Indian Station at Matri, observations were made. There were some amateur and professional expeditions that made it down to Antarctica, but a number of us wanted to see this by air. And so we had knowing that the path was visible from nowhere except Antarctica, made a flight actually very, very appealing, in the sense that the weather prospects actually were quite bad on the ground, and they were quite lucky seeing this at Matra. And other places there was an icebreaker that had gotten clouded out, and some folks here unfortunately were on that one, but they had a great trip down there, but were clouded out of that eclipse. So the path of the eclipse went over, this is the part of Antarctica where we ran the flight right up onto center line, again using the eFlight software, which had been modified for full compliance for use in a Boeing 747 with its navigation system to interface directly in with the flight management computers. And by now, Moore's Law had given us the capability of doing everything on a single laptop. We could stream video guiding for the cameras that we were using on a gyro platform, doing eclipse calculations on the fly, providing navigation information back to the aircraft, running timers, keeping track. This was something that you couldn't dream of 20 years earlier when I started, 30 years earlier when I started eclipse chasing. We had to validate the software before actually plugging it in to the flight management systems on the computer. We went down to Qantas's training facility in Sydney. We ran 4 hours and half a dozen simulations of various conditions. They said, okay, you can do it. We put together a very simple, in some sense, 4-camera system on a single platform to image out one of the windows in the flight deck and the whole back of the airplane, of course, filled with eclipse chasers watching this. All autonomously computer controlled, with a real reliance now on these technologies. The technology is also developed image stabilization made possible by microelectronics and micro-optics to stabilize the image well pointed out of an aircraft window. The introduction of new low noise CCD devices, and this by now is completely obsolete. You know, the better devices and the cameras you can buy for $50 off the shelf today, but at the time was sort of state of the art. And using actually a different technology, these are just reaction wheel gyros, the same kind that are used on many spacecraft today to keep things accurately pointed, here just to keep things stable. They're flywheels is basically all they are. And they keep the platform floating like a small spacecraft when suspended on a bungee cord. The question is, where do you suspend the platform from? This is the window we were going to use. We noticed there was this sort of space above it, so we asked Qantas, could we kind of do something like this, drill some holes in your airplane? And they said no, but we came up with the idea of using vacuum suction cups, a low technology, but actually a very good one. These are just pump-up suction cups, stick them on the wall, they work, and you can hang anything from it. We all got onto the airplane, loaded into 3 separate flight management computers, the baseline intercept plan, and away we went for almost a 12,000 kilometer flight, the longest domestic flight in history because it left and came back to the same place in Australia. Beautiful sunrise over the Antarctic. And you can see just when it was at the horizon, actually looking through some cloud. The pilots complained that our flight plan took them looking straight into the sun. You can see them shielding it, and we reminded them, though, it wouldn't be a problem. It's going to go away in a little while. We had beautiful clear skies over the coastal pack ice as we proceeded inland. Our heading alignment maneuver to get us on track for the umbral intercept. 35-degree bank in a 747, which is a really fun thing to do. This is the perspective from on the flight deck. And so throttled up for the totality run, fired up the imaging program. Here's that camera platform being suspended on a single bungee cord behind the pilot's head, which also made him a little bit nervous. And the Umbra approaching from behind the airplane. And it worked. The imaging cameras sequence, everything fired as expected. This is a guiding camera raw image, processed image, a little bit of additional processing for spatial frequency filtering, getting more information out of the corona. And the point of using multiple cameras is to get different information from different regions of the corona. The CCD camera. This is the film cameras we were running, again, all computer controlled, and then later putting these things together with different levels of processing. There's a beautiful image that was done by David Finley and Miloslav Druckmuller from images taken on the aircraft. And so if people ask, can you get good solar eclipse imagery looking out airplane windows, I think the answer is yes. So I'm going to proceed rather quickly here, skipping the rest of these to show you just two other things. First, the same technologies were applied 2 years later, modifying the platform for a 32-second eclipse, some call a hybrid eclipse. It was in the middle of the Pacific Ocean. This required a ship, not an airplane, to get to. We were quite worried about clouds, and we were keeping an eye on clouds using remote sensing, but this actually came down to just sitting down with the captain and just watching for cloud as we actually had to move the ship at about 14 knots. Same imaging platform that was used on the aircraft, modified a bit, and hanging here from a luggage trolley that I managed to grab for a week. Very close call. As you see, the sun emerged just before totality, but here's an imaging sequence. This is courtesy of William Whidden, who unfortunately is no longer with us. I collaborated on some of the processing of this with, and what we really wanted here was to see this arc of chromosphere because the moon was so well matched to the sun in its angular diameter. And then, of course, the third contact diamond ring. And one of my interests here was in looking at the interaction between the chromospheric level, the transition layer actually, just above the chromosphere and the very inner corona. So if you take an image of the sun and unwrap it, you actually can see it's too low a contrast here, the interaction between the base of the plumage of the inner coronal region and the prominences themselves. And the last eclipse I want to show you today is 2006. I don't have time to show you every one. Sometimes you don't have to go to such extremes for eclipse chasing. In March 2006, many eclipse chasers opted to go to Libya. We actually opted to go to Turkey. The main reason for that is we identified 6 airfields across the path of totality, so we could relocate if we needed to, if the weather was threatening after that somewhat harrowing chase by ship. So we had an aircraft, there's the airport right there, there's Centerline right there. We could have taken off and actually observed from the air by crossing or going to one of those other airfields. The goal here, if we could stay on the ground, which we did, was time-resolved high dynamic range imaging for looking for high-resolution structures in the corona. The path of the eclipse, actually, though, in this case, was not in the middle of nowhere, but was right on the grounds of a 5-star hotel. I joined Rick Brown and his group there, and it was an amazing place because we set up right on a helipad, gave us a perfect positional reference. The high dynamic range, this is a really heavily saturated and pushed image from the 2003 eclipse. This is a brightness profile. This is just towards the edge of the moon, but it shows you how the brightness drops off as you go out in solar radius. These are in decades, powers of 10. And so there's almost a factor of 10,000 from the edge of the sun out to about 6 solar radii in the change in brightness. So in order to accommodate that, the method I've adopted over the years is to use 2 cameras, not try to do it in one. To use a high-resolution camera, long focal length, and low film speed. I was still using film back then, but low sensitivity in order to get into the inner regions of the corona, and a wide-field camera to get to the outer part of the corona. And this just shows you when you put 2 cameras together, you really can get a factor of more than 10,000 quite nicely by doing a ramp of exposures, going short exposures to long exposures at mid-eclipse, and another camera offset with different film speeds, sensitivities, and F ratios. So altogether, you get roughly a factor of 29 from the exposure ramp, from the two cameras being offset, another factor of 67 from the exposure ramp, which gives you a factor of about 2,000 in exposure time across the eclipse. And then the film has a latitude, just as CCD cameras do, of about an order of magnitude or so. That gives you a factor of 20,000 imaging. And so across two different times of the eclipse, near mid-eclipse and near the end of the eclipse, you get pretty much the same sensitivities on two different cameras and then can put images together. An automated imaging system, again, built into a piece of luggage to make it friendly for security at airports. Bringing it off to the eclipse site, and we actually operated a third camera by Joel Moskowitz, who's not here today, as an intermediate focal length camera as a backup. Again, all autonomously controlled, so we can watch the eclipse. And you can see the results of the high-resolution camera. These are actually individual images, as you can actually see the moon moving across during the course of this sort of 4-minute-ish eclipse. The outer coronal camera to capture the outer regions of the corona, individual exposures. And finally, this sort of mid-range camera. And when we put all these images together, just from the different cameras, the diamond ring sequence transitioning at second contact, from the chromosphere, second contact series, you can see the details in the inner corona, both at second and third contact. The motion of the moon, which you normally don't perceive visually, but if you look at sort of the relative motion during the course of the eclipse, and of course you never see the thing in the middle, which is synthesizing the two images together, but it gives you a sense of how much the moon actually moves during the course of a typical total solar eclipse like this, and the mid and outer corona. Brown coming up, he's going to talk about how we use the capabilities for in-flight navigation to extend this eclipse to well beyond what the theoretical roughly 7.5 minute maximum is, to almost 9.5 minutes of totality from clear skies. So the answer to the question that I raised at the beginning, are we eclipse chasers a cult or a culture? I think people in the audience who've done eclipses will agree we'll do just about anything to see an eclipse. We'll go to extremes for building gadgets and contraptions to help us watch eclipses. Does that make us a cult or does that make us a culture? Well, in the true spirit of Moore's law and binary computations, are we a cult or a culture? Putting this thing through a gate, the answer is yes, we are. And there's a recent redefinition of what cult and culture is, and they're self-referential, which is actually sort of interesting to me. Designating a cult defined as designating cultural phenomena with a strong and often enduring appeal to a relatively small audience. Eclipse chasers, as a percentage of the world's population, admittedly, we're a very small percentage. But we all have to go out from here and spread the word, because this is a pathway not only for fulfillment and cultural aspects, but as a jumping point for all the young people in the audience to think about the future of what they want to do. And even if you don't go into science as a profession, this can really get you thinking about the way the universe works. We're not fringe and we are not non-mainstream. So I will disagree with this, and hopefully by the next SED, maybe we can get them to change this definition. So, but it does sound like us. And that's my trip down memory lane. Thank you.